Okay, so hopefully you're coming into this video with an understanding of the basics of what trigonometric functions look like on graphs. You understand some of the basic terminology, and now we're going to talk about how to transform them. I'm hoping for many of you that this is a recap lesson from grade 11 because we are going to move rather quickly. I'm going to do a summary chart on the first page here, and then we're going to do two examples of graphing with a sine function and then graphing with a cosine function so you can see how that lands. The first letter, we've got a lot of different letters here that represent various transformations, and the first one that we're going to talk about is the A out front. The A tells us two different pieces of information when it comes to a transformation. The very first thing it tells us is there going to be a reflection over the x-axis? A vertical reflection. If A is negative, there's going to be a vertical reflection. If it's positive, there's no reflection at all. The other thing it tells us is if there is any kind of vertical stretch or compression. And that is when we're talking literally about a transformation. If you were to list the types of transformations that have happened to a function, you would either use the word vertical stretch or vertical compression. Now, in terms of our graphical property, what it looks like on a graph, we're going to take the absolute value of A, and what that just means is the positive number. So if it's -10, you would just say 10. The absolute value of A is our amplitude. Okay, the absolute value of A implies that it is always going to be a positive number. So if I ask you, what is the amplitude on this graph? The answer is a positive number. The negative out front represents a reflection. It has nothing to do with the amplitude. It just so happens that it's stuck out front at the same time. We use our amplitude, we use our A value to help us determine where the maximum and the minimum points are. And we'll see how that goes when we do our examples. Okay, so that's our A value. The next letter that we are presented with here is a K value. K represents our, once again, two different things, very similar to A. The first thing it's going to tell us is if there is a reflection over the y-axis. And this is a horizontal flip. The A value is a vertical flip, K is a horizontal flip. The other thing it tells us is if there is a horizontal stretch or compression. Now, what that's going to affect at the end of the day is the period of our trigonometric function. And we can determine the period in radians using the formula 2 pi over k. I'm just going to highlight that so that it really sticks out. 2 pi over k is the formula to determine the period of our trigonometric function. How we're going to use this to graph, we're going to use this to determine where the endpoint is. Okay, and that's just going to be for one cycle. Recall that trigonometric functions can go on for infinity cycles. We're only ever going to sketch them using one, sometimes two, but the k value is going to help us figure out where the endpoint is. The next transformation that we have here is this d value, and notice that I am not highlighting the negative number in front. Recall that it's the opposite every time it's like inside the function. The d value represents our horizontal. Ooh, let's write that a little bit neater. You could say shift, or if you want to be real fancy, you could say translation. when we're talking about trig functions, they call translations to the left and to the right. What this might affect is our domain, perhaps, depending on where we're starting at. And it helps us to, so we use it for graphing in terms of determining where our starting point is. H is the last one that we have. And notice that I've highlighted the plus sign this time, and it's because whatever sign that is comes along with the H. H represents a vertical translation. Or a vertical shift. It might affect the range. Right? If there is a shift, then the range is going to be affected. And then last but not least, this tells us the location of the midline. You know what? I'm going to put that under here. Our midline is located at y is equal to h. H also helps us to determine where the starting point is. Okay, and we've got now two letters or two variables that contribute to our starting point. We've got D and we've got H. Our starting point for sine functions is located at D, comma H. That's where we start. So let's put all of this into practice now and let's actually graph a sine function. And we're going to be using what I call the 5-point method. Maybe it's officially called this, I don't know, but this is where I'm starting. And I've listed the steps up top that we're going to follow, and we're going to do it all together for this function. So we've got the graph y is equal to 3 sine of 2x all minus 1, and we're being asked to graph for 1 cycle. Okay, we're going to do a couple of things here. We need to figure out how high and how low our graph is going to go, and we need to determine the period, okay? Let's start with period first, why not? Recall that the period is 2 pi divided by k, and our k value in this instance, I'll highlight it, is 2. So our period is going to be 2 pi over 2, which is just pi. That's going to help me set up the axes on my graph here. I have no horizontal shift, only vertical shift. And so I'm going to start at 0 and I'm going to end up at pi. So nice and quickly, I'm going to just add a scale to my graph here where pi is the upper limit. And then I'm going to split this down. I'm going to add a pi by 2 and then a couple of pi by 4s. You always need at least 4 numbers on your x-axis, sometimes 5, in order to graph successfully. Okay. The other thing that we need is we need to figure out how high our graph is going to go and how low it's going to hit, so that we can add our scale along our y-axis here. We're going to determine our midline. Recall that the midline formula was y is equal to h, and h, in this case, is -1. So our midline is at -1. We can determine our max. I'll just do max in black. And our min. We start at our midline. And for our max, we need to go up by our amplitude. In this case, our amplitude, A, is 3. So we need to go up by 3. My max, I'm going to go up -1 plus 3. Midline is going to go down by 3. So the highest point my function is going to reach is 2, and the lowest point is going to be -4. I can use that to set up my graph accordingly. Okay, I only need to go down so far as -4, so I'm going to put -4 all the way down here and fill in my y-axis this way. Okay, so we've done a bunch of the background information. Let's go ahead and start. I'm going to start at my starting point. Our starting point was at DH, which is 0, -1. I have no horizontal shift. My vertical shift is -1. And so I start at the starting point, and I'm going to put a dot there. 0, -1 is right here. Now I need to add the midline. I'm going to do the midline in just a dotted line here, and our midline was at -1. Recall that we do not draw an actual straight line because it is not a part of your graph. It is just a guiding line. Okay, so we've started our starting point, we've added the midline. Now I need to determine where the last point will land using the period, and I'm going to put a dot on the midline. Well, my period is pi and I'm starting at 0, so I'm going to land at pi. I put a dot on the midline because it comes on back to the midline. Remember that a sine function looks like an S. Okay, check. Now I need to determine the halfway point between the start and the end of the first cycle. Halfway between 0 and pi is pi over 2, and I'm going to put a dot on the midline. Okay. Last but not least, I need to find the two other points. They're going to be halfway between the start and the middle, pi over 4. And then it's also going to be in the second half right down the middle, 3 pi over 4. I need to place these points at the max or the min based on the altitude. I've already determined the max and the min. And these are going to be affected if there's a vertical reflection. In this case, there's not. So I do follow the typical sine function. If there had been a vertical reflection, I would go down first instead of up. But here there's not, so I go up first and then down. Okay, so my first dot is going to be located at the max, which is at 2. And my fourth dot is going to be located at the min, which is at -1. Okay, the very last step that we have to do here is we literally just have to add the line. Recall that it's supposed to be smooth, not zigzaggy. So we're going to try and keep it as smooth as possible. And that's it. That is our function, our trigonometric function, all transformations included. All right, let's do a second example now involving our cosine graph. Okay, let's take a look at the function we've been given. Y equals -2 cosine of 3x plus pi, all take away 1. First thing I notice here is that my brackets are not in factored form. They need to be in order to determine both the horizontal stretch and the horizontal shift. So I'm going to go ahead and factor that. I can pull out a 3, leaving me with x plus pi over 3. All take away 1. Beautiful. Let's figure out a couple key pieces of information here from our function before we move on to anything. Okay, we'll start with the period. Period was 2 pi divided by k, and in this case our k value is 3. So our period is going to be 2 pi over 3, or 2 over 3 pi. No, I'll just leave it as 2 pi over 3. We can find our midline. That was at y is equal to h. H in this example is -1. We can see that there is a vertical reflection. So that means that our graph is going to take the shape of this like funky N. And I can also see that there is a vertical stretch, which is going to affect our max and min. The vertical stretch tells us our amplitude, which is 2. Let's figure out max and min. We always start from the midline, which is -1. Max, you add the amplitude. Min, you subtract the amplitude. So in this case, our max is 1, +1, and our min is -3. We have a horizontal shift here of -π/3. And our period is 2π/3. So the total distance traveled, okay, like the horizontal span that I need my graph to go, we're going to start at -π/3, but then go over 2π/3. So we're going to end at +π/3. I'm just going to write that down here. Our endpoint. Start at -π/3, add 2π/3. -π/3 comes from that shift, and I add the period, which is 2π/3. To figure out where we're going to end, our endpoint is +π/3. So just by looking at this graph, we can now start to fill in our axes. The furthest left we're going to go is -π/3. The farthest right is π/3. So I'm going to take that to my advantage, and I'm going to make the farthest sort of thicker lines my π/3. And then halfway I'm going to add in a π/6. Vertically, I only need to go as high as 1, but I do need to go as far down as -3. So I'm going to add, I'm going to be counting by halves here. To fill in my axes. Let's graph. I think we've figured out all the information. So step number 1, start at the max or min based on the horizontal vertical shifts, vertical stretch, and if there's a reflection. Well, we've already said that there's a reflection. So I'm going to be starting at the min. The min was affected by not only my shift or my midline, but it was also affected by my amplitude, which was 2, and we've located the min at -3. So the lowest point where I'm going to be starting at will be my horizontal shift, and then the min, -π/3. I'm going to be starting right here. Now I need to place my final dot based on the period. We've determined that the period is 2π/3, and we've even gone so far to say, well, we're going to end up at π/3. Given the shape of the graph, I end at my min again. So at π/3, I land down here. Check. Now we need to figure out the halfway point between the start and the end of the cycle. Well, halfway between -π/3 and π/3 is just 0. That's nice and easy, okay? Place a dot at the max. Alrighty, the max is 1. I'm going to place a dot right here. Now I need to add the midline, and I'm going to add that as a dotted line, a guided line. And my midline we already found is at -1. Beautiful. Check. Find the other 2 points, place them on the midline. So my other 2 points are going to be halfway between these two, which will be at π/6, and I put a dot on the midline. And then my second, or my fourth point, I should say, is going to be halfway between this guy and this guy, which is at π/6. I put a dot on the midline. Check. We've got 5 dots now. We can go ahead and sketch. And recall, it's not a triangle. It looks like it could be, but it's not. It's a little curvier. And that is our cosine function. We've included everything we need to include. It is fully transformed. Okay? It's going to take a bit of practice to get used to this method if you were not familiar with it before, but I promise this is the most efficient and the easiest way to quickly sketch transformed sine or cosine functions. The last thing I'll mention is tangent functions. Tangent functions are the third one when we talk about trigonometric functions. However, they're very rarely used. Most periodic functions, or I should say many periodic functions, are either sinusoidal or cosine. And so we don't really practice transforming them. If you think about how they look, they're just a bunch of squiggly vertical lines, and there's not much that would change about them if you were to transform. You could transform them, absolutely, but we're just going to focus here on sine and cosine because they're the more common and the more frequent ones.